It's already 35. Yeah, okay, good afternoon. So as I sent the email, so we'll, you have seen the email, right? There was one by... So the goal today is to have a little more. So we did lecture 1 intro, lecture 2, 3, 4 regression. Can talk outside, that's okay. So regression, there were a little bit about regularization left, which we'll do tomorrow, because today I've kept it only for background for the non-CS people. That's the plan. So tomorrow we'll finish that 4 slides on regression and start support vector machine intro, then do a support vector machine example. So that's the plan. On the drive, I've already uploaded a little more material. The next 2 lectures are there, of course. Then Scribble, though you keep looking at it, there's not much to look at. Then tutorial lab, I've put the next one, regression. This you can start looking if you want. If you have time, you can take a look. And then in the offline part, we'll do this constraint optimization today. And practice problems you can try now. I think we've finished most of the regression, so you can try. I think that's it. Okay. So let's start constraint optimization. Okay. So again, the idea is when we start support vector machines tomorrow or on Wednesday, we'll start using this optimization theory. So it's important that you know this. So the CS UG people, I asked them not to come because they have seen it with me. So I think this is the only extra lecture I am taking, the second one. If needed for the distance-based model, I may take one more, but there are not too many, so you should not get overwhelmed. So we have already seen unconstrained optimization. So in the what is unconstrained optimization? Sorry? Only objective, no constraints are there, right? Constraint optimization is that there is some sort of a constraint there. And what was the necessary condition for finding a minima in the case of unconstrained optimization? Gradient is 0. What was the sufficiency condition? Hessian is positive definite, right? Gradient 0, Hessian positive definite implies it's a strong local minimizer, which is just coming from the case of f going from 1 to 1, f prime equal to 0, f double prime greater than 0. In the case of a multivariable f, in f having a multiple dimensions in the domain and single dimension in the range, it becomes gradient and Hessian, right? So now we'll see a little more complicated form of this, because now we have constraints as well, which means that you're not just looking at the objective function in all of the space, but there's some bounded space on which the solution exists, and there we're looking at. So what I have shown here, I'll do it in 2 parts. One is when you're looking at the specific case of only equality constraints. Is it readable at the back, or should I make it bigger? Readable? Okay. So minimize f of x subject to ai of x equal to 0. What could be the other constraints? It could be greater than equal to. So the most general form is minimize f of x with respect to x subject to ai of x equal to 0 and cj of x greater than equal to 0. So this is referred to as the equality constraints, and this is referred to as the inequality constraints, and f is going from n-dimensional space to a one-dimensional space. The range is always 1. If there are multiple ranges, it's the case of multi-objective optimization, where you can take different objective functions and minimize separately. But the domain is something which is more critical to us. So right now what I am talking about is this case, where we only have equality constraint. So what does the first order necessary condition in this case say? That if x star is a local constraint minimizer of above and is a regular point of star. Now this comes in the theorem. What is a regular point? Regular point means you take the gradients of the A's, the constraints, and if they are linearly independent at x star, it is a regular point, which I have written it in red. But you don't need to worry about it too much because mostly it's regular. So what are the two conditions? The first condition is that AI of x star is equal to 0, which is obvious. It has to satisfy the constraints, right? The second is that the gradient of the function is a linear combination of the gradient of the constraints. If there was no constraints, what will happen? This right hand side would be 0. We'll go back to the unconstrained case, which you have seen with me earlier. Yes or no? And of course, A will not exist if there was no AI, the A condition. Correct? So let's see how we'll apply it to a problem. We'll apply it to two problems. Then we'll go to the most general form, which we are going to use in the support vector machine, that minimize the function with respect to equality constraints as well as inequality constraints, which is where we are going. So if I have to apply this, we're saying minimize x1 plus x2 subject to x1 plus x2 square minus 2 equal to 0. This is my objective function. This is my constraint. This is a function going from a two-dimensional space to a one-dimensional space, x1 and x2. So what is the gradient? Differentiate with respect to x1, which is 1. Differentiate with respect to x2, which is 1. What is the gradient? Now we have to compute the gradient of the constraints as well, because they are constraints too. So which says that gradient of this guy will be 2x1, gradient of this guy will be 2x2. Correct? So which means now the condition says that first you have to of course have this to be true. And the second B condition says you have to equate the constraints and multiply with them a constant in front. The proof of this is in these slides, but you don't need to understand it. I mean, it's basic geometry, algebra, linear algebra proof. There is nothing complicated about it, but I'm not doing it for the machine learning class. For you, the theorem is given to you, because you have to use that in support vector machine. So the gradient of the function is lambda times, so this is gradient of the function, lambda times gradient of the constraints, and we are able to equate it that x1 is 1 over 2 lambda, x2 is equal to 2 over lambda. This is coming from the B condition. The A condition is saying that this is equal to 0. Everybody with me? So what will I do? I'll take this x1 and x2 and substitute into this and solve for x1, x2 and lambda. Correct? So that's what we do on the next page. We take x1 square, this is the A condition, we substitute x1 is 1 over 2 lambda, x2 is 1 over 2 lambda, so square of that, and we solve for lambda, we get 2 lambdas, plus or minus half. Once you substitute this into x1 and x2, which is on the previous slide, then you get the one point as 1 comma 1 and the other point as minus 1 comma minus. So the function value here is 2 because it's just x1 plus x2. Again, it's just minus 2 because it's x1 plus x2. So which means that it's giving you candidates for minimizer. It is also giving you the candidates for maximizer. So one value is, it's a stationary point basically. It could be minimizer, maximizer, or the point of inflection where the curve just changes, no? So it could be any, but it is still a candidate. I have not applied the sufficiency conditions. Everybody with me? Why don't you do the next problem and see if you have understood this, because I'll do this in a more general form in SVM. So this should be clear in your head. So this is given to you. Function is now going from a three-dimensional space to a one-dimensional space. There are two constraints, A1 and A2. So we'll find gradients of these. We'll find gradients of these. Now what will you write? Gradient of this is equal to lambda 1 times gradient of this plus lambda 2 times gradient of this. So how many equations will you get? 3 equations, and then you need 2 more equations. They will come from the A conditions that the constraints are equal to 0. Correct? So how many equations do you have? 5. How many variables do you have? 5 variables, right? x1, x2, x3, and 2 artificially created variables, lambda 1 and lambda 2, which are the Lagrange multiplier. Why the name? I could call it couple multiplier. It was the French mathematician who 100 years ago figured it out that this is how it should work. His name was Lagrange. He has contributed to many other areas of mathematics, so hence his name Lagrange multipliers. Is that okay? Can you solve it? Try it, so that you understand what I am trying to. I'll show you the slide as we go along. At least work on one problem, because after this it gets more complicated. Lab was okay for everyone? So this lab on Thursday, we'll do 4 problems on regression, and then we'll start searching for your papers for your survey paper, which I said 30% mid-sem, 10% quiz, and 10% survey paper. So I'll show you the list of journals where you should look. Don't do a Google search. You'll end up getting open access junk journals, many of them. I mean, if you are an advanced student, you would know where to, which is good quality, which is not. I would want you to look at the topmost journals in machine learning and make a survey out of it. So we'll talk about that more on Thursday. Okay, did anybody solve it? So I'll just go a step further. So this is what I said, gradient of the function is linear combination of the gradient of the constraint. So you write the gradient of the function, gradient of the first constraint, gradient of the second constraints, and you get 3 equations. And they get 2 more equations from these guys, A1 and A2. So once you write that, so you get 5 equations. I mean, these are not per se linear equations because they are 2 quadratic equations, but you can solve them easily. It is solvable by hand. Did everybody reach this stage? Okay, so we'll not let you worry about the rest of the algebra. I'll move forward. So once you solve it, you get 2 candidates. And when we apply the sufficiency conditions, which I have not told you in the case of constraint optimization what it is, we'll tell you at the end. It will turn out that one is a minimizer and other is not a minimizer, like we saw earlier. Right now it is still a candidate for minimizer. ठीक है? Okay, all right. One more problem, this you do it at home. In my optimization class, I do it myself in the class, but for you just practice it, because for you this kind of quadratic problems, although we'll see in SVM, but you'll not run into this complexity. So it says that minimize X transpose HX, X transpose Q subject to AX equal to B. You know that H is an n cross n matrix and it's symmetric positive definite. A is full rank, it's R cross n. So rather than working with specific 1, 2, 3 dimensions, you have an n dimensional problem, and this is general. Now the question is, apply the first order necessary condition on this and find the candidates for minimizer. So you go home and please read it through. For the sake of time, I am skipping this for the moment. Once you do that, this will be your candidate for minimizer. Lambda is equal to this. So you can see it looks a little hairy, but when you will give 15, 20, 30 minutes working it out, this will be clear to you. And it's not complicated. If you find it difficult, ask me in the next class. Tomorrow, I mean, after class, you can ask me. Okay. Having said that, now let's move to the general case. So this is the proof. Again, the proof is not for you. Like I said, it's basic geometry and linear algebra. If you are interested how all of a sudden gradient of function is equal to gradient of constraint, this proof tells you why we do it. So I'm skipping this again. In the optimization course, we do it. Now let's get to the conditions which we are going to use in SVM, the most general form. So the general form is this now, minimize fx subject to equality constraint and inequality constraints, which is written here at the top. So there are 5 conditions necessary now, which we are going to use. So let's try to understand. So they are referred to as the Karush-Kuhn-Tucker conditions based on 3 mathematicians who found it. Karush, Kuhn, Tucker, they were 3 people, so that's how. So it says if x star is a local minimizer of the above and a regular points for the constraints that are active at x star. Now, local minimizer, you know, we have discussed that in the last one, local and global. We are usually after local unless it's a convex problem and the local becomes global, right? Regular, I just said that the gradient of the constraint should be linearly independent. In the previous case, gradient of A1, A2, A3, you put them as vectors, and if they are linearly independent vectors, it's a regular point. Here it changes to regular points for the constraints that are active at x. Now what is active and inactive? I usually tell. So let's say I've got 3 constraints. These are all inequality constraints. So this is C1 of x equal to 0, C2 of x equal to 0, C3 of x equal to 0. And this is C1x greater than equal to 0. This is C2x greater than equal to 0. And this is C3 of x greater than 0. So basically the feasible region is, if they were colliding, this is the feasible region inside. So if I take a point somewhere inside, then I'll say all the 3 constraints are inactive. Inactive because at this point C1 is strictly greater than 0, C2 is strictly greater than 0, C3 is strictly greater than 0. Correct? If I take a point at this intersection, then what do we have? We have got C1 is equal to 0, C3 is equal to 0, and C2 is strictly greater than 0 because you are inside the C2 region, but you are at the boundary of C1 and C3. So you will say that C1 and C3 are active at this point and C2 is inactive. Is that okay? So this constraint says above is a regular point for the constraints that are active at x star, which means that of all the Cj's, all may not be equal to 0 at x star. Those which are equal to 0 at x star, you will find their gradients, combine with the gradients of the equality constraints and show that they are linearly independent. Is that okay? Agar regularity confuses you, you can ignore it. For the moment, we don't need it. I'm just telling you so that you know there is some constraint there. What is more important for us are the 5 conditions. So now let's try to read those 5 conditions. Again, we are not doing the proof for this. You should be able to apply this, which itself is a little challenging. So what are the first A and B conditions? A and B are just satisfying the constraints, right? AI of x star equal to 0, Cj of x star greater than equal to 0, which means that you are inside the feasible region. Feasible region is where the constraints are valid. Is that okay? What is the C condition? C condition, we call it as the Lagrange multiplier condition. If you recall the case of only the equality constraint, then this guy was not there. Correct? It was only gradient of the function as linear combination of gradient of the constraints. But now you've got inequality constraints as well. So we're going to add those up in this equation as well. And we'll add different Lagrange multiplier, which we'll call it as mu. Just to separate the equality constraints Lagrange multiplier and the inequality constraint Lagrange multiplier. So we're saying gradient of the function is equal to linear combination of the equality constraints plus the linear combination of inequality constraints. The constants coming in front of the gradients of the equality constraints are Lagrange multipliers corresponding to the equality constraints, which are referred to as lambdas, lambda i's, because we are referring to i's as the equality constraints, and the j's are the inequality constraint, j going from 1 through s. So we are referring to as mu j's. Is it making sense? This is I, this is j. So that's why lambda I and mu j. Everybody okay? So A, B, C are very intuitive. They are just going from what you have seen before, in the unconstrained case or with equality constraint and now with inequality constraint. There's extra 2 conditions which get added here, which are the D and E conditions. So the D and E conditions are referred to as the complementarity and the non-negativity constraints. So the D condition says that the product of the Lagrange multiplier with the constraint should be equal to 0, both for the equality and the inequality. And it also says the E condition, non-negativity, that the mu's, which are the lambda, which are the Lagrange multiplier corresponding to the inequality constraints, they should stay non-negative. Is that okay? So those are the 5 conditions. How we reached it, what's the proof, is out of the scope for you as a non-CS major. The math person who's there may understand this more easily. You can talk to me after class if you need to understand. But now the question is, how can this be simplified? Can somebody tell me there is one condition in this which is redundant? Can anybody notice it? We'll start applying this to real problem, to a test problem, and then tomorrow we'll apply it to support vector machine. That is why I'm spending so much time on this. So tell me, what is the redundant equation here? Think. Tell me, nobody is able to see it? Correct. Yeah. Why do you need this? Because you already have AI of x star equal to 0, so this will automatically be satisfied. So you don't need the first condition of D. Can everybody see it? Okay. All right, so now let's move forward. So now what we'll do is, we'll apply this to a problem. Applying this, because we have to do that tomorrow in SVM, so let's see how to apply this. So if you were not studying a machine learning class, you were taking a blog and trying to use SVM, then you would not worry about how an SVM works. But in the machine learning class, we are worried about this model called support vector machine. And that is why we need to know that it formulates an optimization problem inside. And then it solves the optimization problem inside and then gives you the results. So that is why we are doing this. So let's say this is my problem. This is the objective function. It's a two-dimensional problem. Domain is two-dimensional. They are only inequality constraints. There are no equality constraints. Make it simpler for you, although they could be equality. Everybody understood equality and inequality? That difference? Okay. All right. So now we'll write the 5 conditions. So there is no A condition. There is the B condition, which is the just satisfying the feasibility condition for the inequality constraint. Then we'll write the gradient of the function is the linear combination of the gradient of the constraints. Yes or no? So what is the gradient of the function? This is 2x1, 2x2, 2x1. I think ये गलती है यहाँ. This should be x1. This should be x1. So it's 2x1 minus 14. And this is 2x2 minus 6 with respect to x2. When you differentiate this with respect to x1, you get minus 1 with respect to x2 plus 1, with respect to x1 minus 1, with respect to x2 minus 2, and then you write it down. So this is the C condition. Now the D condition is the product of the Lagrange multiplier and the constraint is equal to 0. Similarly, this guy, and then the last is the non-negativity that both mu's. Why do we have two mu's? Because we have two constraints. Remember, these mu's are corresponding to the constraints. There are two constraints or two mu's. So both the mu's should be non-negative. Now you've got so many equations. 1, 2, 3, 4, 5, 6, 7. And how many unknowns you have? 4 only. x1, x2, mu1, mu2. So in that sense, it seems that you've got too many equations and less unknowns. But these equations are not equalities. These are inequalities. These are greater than equal to, which means that they don't solve like a linear system of equations. If you try to solve them brute force, then you may not end up anywhere. You can practice that at home. So what's the easiest way of solving this, which support vector machine does implicitly in the code also, is make cases, which makes your life easier. Why do we make cases? We make cases because of the D condition. Now what is the D condition? It says the product between the constraint and its Lagrange multiplier should be equal to 0. So what it will get us, it will give us a lot of degree of freedom if we start with the D case. So let's see. We say the first case is, let's say both C1 and C2 are inactive. What C1 and C2 are? They are here. They are inactive. What's the meaning of this? They're strictly greater than 0, not equal to. They are, between, they're inside the feasible region. So what will this buy you from the D condition? If C1 and C2 both are strictly greater than 0, what do we know about mu1 and mu2 from the D condition? Sorry? Mu1 and mu2 have to be 0, right? Otherwise this D condition will not get satisfied. Everybody with me? Can you see it? So it makes our life simpler. Two variables automatically become 0. Now we check for the other whether all the B and C and E are satisfied or not. So we go one by one. So mu1 and mu2 both become 0 from D. We substitute in C. Now you make this equal to 0, make this equal to 0. You'll get x1 is 7 and x2 as, this is 2 by the way, x2 is 3. Correct? So you get 7 and 3 now, but you have to check whether the point is feasible or not. So you'll substitute in the first 2 minus 7 minus 3. That is minus 8. Is minus 8 greater than equal to 0? No, it is less than 0. Which means the point, although you have found it, it's not a feasible point. It is satisfying the non-negativity, that's not a problem, but it's not satisfying the B condition. So hence this case fails. How many cases do we have if let's say we have got n constraints? How many cases will we have? 2 to the power n, because for every constraint it will be either active, inactive, active, inactive, active, inactive, and you'll multiply that. Correct? So here there were only 2 constraints, so the number of cases are 2 to the power 2, which is 4 cases. Okay, so now one case you do it and tell me what do you get. So the next case you do it, I'll not show you the answer. It says C1 is active and C2 is inactive. So if C1 is active, which means that mu1 can be anything. This is equal to 0. It's given to you. And C2 is inactive, which means this is greater than 0, but mu2 becomes 0, which is written here. Can you solve it now? The case B. Do it with me once, because like I said, tomorrow when I do it, it will come all of a sudden, because I'll do it in a general form. I'll not do it for a smaller problem. Okay, this one, let me do it. You do the third case, because you're seeing it for the first time. So let's just do it. So we say mu2 is equal to 0 because C2 is inactive. This is greater than 0, so mu2 has to be equal to 0. Everybody with me? So we'll go back to now the case that we know 2 minus x1 minus x2 is equal to 0. This we know because the first constraint is active. And we also know these condition, and in this one we know mu2 is equal to 0. Correct? So we'll write 2x1 minus 14 is equal to minus mu1, 2x2 minus 6 is equal to plus mu1. So we get three equations, three linear equations and three unknowns. And we can easily solve for this. Yes or no? So once we solve it, we get x as 3 minus 1, mu1 as 8, mu2 we already know is 0 because we have forced it. But we need to check whether we are satisfying the B and the E condition. The feasibility condition and the non-negativity condition. Whether we are satisfying the feasibility condition for both and we are satisfying the non-negativity. The non-negativity is obvious, you're satisfying because both mu's are 8 and 0 are greater than equal to 0. But we have to check for the B condition. So if you check for the B condition, so you get that this condition is true. The first feasibility will be true because you solved it by making it equal to 0. Yes or no? You have to just check for this guy. So substitute 3 and then you put what's the value of x3. So 3 and 3 will cancel and there is x2 is minus 1. Minus 1 times minus 2 is plus 2. Is 2 greater than equal to 0? Yes. So it satisfies. Hence, this is a candidate for minimizer. Everybody with me? Now do the next one. है ना? एक I wanted to show you. You do this one. Only C1 is active and C2 is inactive. Now we're switching sides. Can you work it out and tell me what, do you get a candidate for minimizer or you don't? Actually, this is, I want to hide this. Don't look at it. है ना? नीचे का. So you make the first constraints to be inactive, which means that mu1 will be now 0, but mu2 is active, which means that the mu2 constraint will be equal to 0 and mu2 can be anything. Can you solve for it? It's not solved here, so you can actually solve it. So from the D condition, we get mu1 is equal to 0, mu2 could be anything. Then we go to the C condition. The C condition was, so we'll put mu1 equal to 0. So we'll put 2x1 minus 14 is equal to minus mu2. 2x2 minus 6 is equal to minus 2 mu2. And since C2 is active, so we also have 3 minus x1 minus 2x2 equal to 0. Correct? Everybody with me? Can you solve for this and tell me what you get? So how many of you were undergraduate mechanical? Raise your hand. Mechanical and electrical, MEMS and civil. Okay. So you tell your friends that why are they taking this class? They should drop it. If they're not interested in studying, I'm taking an extra lecture to make you, first of all, I allowed everybody to sit so that it will help you. Then I'm taking an extra lecture to get your background done. If you just want to come, take a class for the sake of it, take an humanities school. Why you're taking slightly harder? Tell them, Anna. I mean, why are not they're not here? I'm covering a background which will be useful tomorrow. SVM will not make any sense if they don't attend this. So it's unfortunate. CS, though I asked them not to come because they've seen it. But if the undergraduate students, I don't worry because they will learn anyways. It's their thesis or their PhD or masters. Undergraduates should come, hai na? Mechanical, at least the strength is there. MEMS, only 3 people are there. So it's very unfortunate. Okay. Never mind. Did anybody solve? अभी तक solve ही नहीं किया. क्या है रहा है? x1 is 5, x2 is? And mu2 is? 5 2s are 10. 10 minus, ठीक है, यही आ रहा है क्या? नहीं, यहाँ तो ये आ रहा है आंसर. ये भी एक कैंडिडेट आ रहा है क्या? दिस इज 5. हाँ, ये आ तो रहा है. मे बी दिस इज नॉट कमिंग क्या? So are we getting 2 candidates क्या? This is also coming. Did anybody got 14/3? Did anybody get this? मैंने कुछ गलत लिख दिया है लगता है. Chalo, anyways, you solve it. It's not complicated. You will get this, but one of the constraints will not get satisfied, and then you will get that this violates. है ना? So we did the C condition, and then ये कुलदीप ने ठीक तरह लिखा नहीं है. We should have checked for. Now we are taking C2 as active, so we'll have to check for C1 with this value. When we put this value in C1, 14/3 minus 5/3. 14/3 and minus 5/3, it will not turn out to be, something will violate here. So this will not give you the candidate for minimizer. When you do both cases are active, also it will violate. So the only case which will work is this will give you a candidate for minimizer. You can check, hai na, if you get these cases, you can check whether they are satisfying or not. Hai na? Should we move on? Everybody okay that you have to do cases? Tomorrow when we do support vector machine, we'll first take the model, the geometric model. Now we move from regression to another model. We'll formulate it as optimization, I'll show you. And Wednesday then we'll solve it. We'll first solve it generally, then I'll give you a short example, 3x3, and then we'll use the same logic. There'll be 3 constraints, so we'll get 8 cases. We'll not solve all the cases, but we'll show you. Right? Okay, so now what should we do next? Can somebody tell me what is left now in this part? Just to wake you up, just to check that you are awake. Are we done or there's something remaining? Are we done? Yes? No? You can guess there's something left. There's time left and I've not. So there's something left. Can you close the door? So what is left? What did we do in the case of unconstrained? Okay, what did we do here today? We took the optimization problem, a constrained optimization problem, and worked first with equality constraint. Minimize f of x subject to ai of x equal to 0, I going from 1 through n. And then we applied the first order necessary condition, which was that ai of x star equal to 0 and gradient of the function is linear combination of gradient of constraints. Gradient of f is equal to summation lambda I gradient of ai. That was the. Then we moved on to the general case. The general case said that you have to satisfy the two A and B conditions, which are the feasibility conditions. AIF is equal to 0, CJX star equal to 0. The C condition, which is the Lagrange multiplier condition. Now the gradient of the function is linear combination of gradient of both the constraints, equality, inequality. You had the D condition, which was the complementarity condition. For the inequality constraint, the product between the Lagrange multiplier and the constraint has to be 0. And the E condition, the non-negativity on the mu's. So, but what all we did was just necessary? Yes or no? What do we need to do now? Sufficiency. We are always just getting you candidates for minimizer. We want a minimizer. Yes or no? So, we'll go to the sufficiency condition. I'm going to show you that. Is that okay? Okay. I used to tell that I used to crack jokes, but now so few of you guys are coming and feeling very disappointed. डॉक्टर कहिए कैसे आना हुआ? राजू डॉक्टर साहब लीवर में बहुत दर्द हो रहा है. डॉक्टर शराब पीते हो? राजू हाँ हाँ बिल्कुल, पर छोटा पैक ही बनाना. So that's the joke. So at least you guys are not sleeping because you're interested. So now we go to the sufficiency condition. I'll skip the second order necessary, like I skipped the second order necessary in the case of unconstrained. What is second order necessary? Second order means that you're working with the second derivative, but it's still necessary. Necessary means it is a minimizer, then what? But what we are after is the sufficiency condition. What are the conditions for it to be a minimizer? है ना? So I'm going to skip the necessary condition second order. We'll just go to the second order sufficiency condition, both for the case of AIX equal to 0 and the general case AIX equal to 0, CJX greater than equal to 0. Everybody with me? Okay. So let's look at the condition. So it says if x star is a regular point of constraints, this is equal to 0 and this is equal to 0, and there's something which I'm going to tell you now what it means, then x star is a strong local minimizer. So what happened? You got one more condition and you were able to bring sufficiency. Why sufficiency? Because it's going the other direction. If this is true, then it is definitely a minimizer. Are able to separate the two, like I separated the necessary and sufficient last week, that what is the necessary for being in CS undergrad at IIT Indore. There are many necessary conditions. You have to clear 12th, you have to get some marks, you have to sit for JEE mains. All these are different necessary conditions. But when you have to get sufficiency conditions, you have to add all of them. If you pass 12 with certain marks, sit for JEE mains, get into 100,000, sit for JEE advanced, get into 2,000 or 1,000, whatever rank, come for counseling, pay your fees, join the mess, come to the hostel, everything, then you will be sitting in my class and taking lectures. So those are all sufficiency. So similarly, this is a sufficiency condition. If AI of x star is equal to 0 and the B condition, the two necessary conditions, and there's something more, the C condition, then it is a strong local minimizer. If you look at the C condition, without I'm explaining you further, there is a Hessian playing a role here. Again, you can see the Hessian written there, which means that you're going to the second order or the second derivative or the second degree, whatever you want to call it, which means that it is a second order sufficiency condition. Is that okay? This was for the case, I'll explain you the C condition, but this was the case when only AI of x is equal to 0. F of x with AI of x is equal to 0. That's the objective function. When it's the general form, what happens? You got A, B, C, D, E, which you have just seen with me today. The feasibility, the Lagrange multiplier, the complementarity, the non-negativity. And then I've added another F condition. This F condition is same as the C condition in the case of only equality constraint, where a Hessian is playing a role. Is that okay? So this and this is the same. Okay, so now I'll tell you what this means. Okay? So To tell you this, I'll have to tell you what is a Lagrangian. So let's look at first this case. It says Hessian of the Lagrangian with respect to x is positive definite over null space of Jacobian of constraint. Looks a little hairy. By the way, the good news is that you don't need to understand this for tomorrow's SVM. I'm just telling you for the sake of completeness so that you know there is a necessary and there is a sufficiency. What will happen in the SVM case tomorrow or in the machine learning context, our problem, the necessary conditions will become sufficiency because our problem will be convex. So these sufficiency conditions will not apply tomorrow. But I still want to tell you so that you have the complete picture of that there is a sufficiency condition as well and what it means. Is that okay? So let's try to just understand it. Again, why, how this is coming and where this is coming from is out of scope, the proof of this. I just want to use so that you can read a sufficiency condition. So what is Lagrangian first of all? So if you recall, the necessary condition, the first order necessary, this is the case which we are doing this case, that we only have equality constraints. So you've got minimize f of x with respect to x and subject to only equality constraints, ai of x equal to 0, I going from 1 through r, whatever. The first order necessary condition besides the blah blah regularity was that ai of x star at that point should be 0, and b, the gradient of the function at x star should be a linear combination of the gradient of constraints. अब तक तो याद हो गया, we've done it 3-4 times now, है ना? So these are called Lagrange multiplier because of the Lagrange, who was the French mathematician who found this. So he also defined a Lagrangian function first. So what is a Lagrangian function? A Lagrangian function goes like this. It says it's a function of x, which is the variable, and lambda, which are the Lagrange multiplier. It's nothing but gradient f of x minus summation lambda I ai of x. This is a Lagrangian or a Lagrange function. That is how we write. Now if I have to write this guy, what will I do to this? What kind of derivative should I take of the Lagrangian function to get the A condition? And what derivative should I take to get the B condition? Can somebody think with me? Correct. What's your name? Are you from math? Yeah, okay, that's fine. So the A condition is coming if you take the gradient of the Lagrangian with respect to lambda. How many lambdas do we have? R lambdas, because we have got R constraints. You have to take partials with respect to lambda and make it equal to 0. So if I say dl divided by d lambda 1, what will this be? This will be 0, there is no lambda. This would be 0. A1 आएगा ना, scalars हैं यहाँ पे, we are making this equal to 0, then this will be equal to 0. If I do gradient of the Lagrangian with respect to lambda 2, what will I get? A2. Which means that if I do gradient of the Lagrangian with respect to lambda, then I'll get just ai of, and then all of that I have to make them equal to 0. So we'll get the first condition. Correct? Second condition कैसे आएगी? If I do gradient of the Lagrangian with respect to x1, what will that be? It will be partial of x1 minus summation lambda I partial of ai of x with respect to x1. Correct? If I do with respect to x2, there will be partials with respect to x2. If we'll do xn, sorry, they are nx, there will be xn. Everybody with me? So this will go like this, which means that if I have to write the gradient of the Lagrangian with respect to x, it will be gradient of the function which is with respect to x, you write or don't write, doesn't matter, because f is a function of x only, there is no lambda here, minus summation lambda I gradient of ai of x. You write x here or don't write, doesn't matter, because a is again just a function of x. Yes or no? So we got the second condition by taking the gradient of the Lagrangian with respect to x. We got the first condition by taking the gradient of the Lagrangian. So this guy gives us this. And this guy gives us this. Correct? Yes or no? Everybody convinced? So the two together, if I have to write, I would just write that the gradient of the Lagrangian is equal to 0. Because Lagrangian is a function of x and lambda, which means that you will do with respect to lambda, you will with respect to x and make it equal to 0. This becomes the necessary condition. Is that okay? Now you have got the gradient of the Lagrangian. Now you have to do the Hessian of this. But the problem says do it with respect to x. So once you have got this gradient of the Lagrangian, which would be a vector like this, which will be a function of both x and lambda, because it's a function of x and lambda, you differentiate all of them only with respect to x. Because you have to compute the Hessian, the second derivative, with respect to x. Whatever matrix which will result out of this, Hessian of this with respect to x, there will be a matrix which turns out. You have to show that this matrix is positive definite over some space. Is that okay? Now what is that space? Let me tell you. Is that okay? Now what is this J, which I have not told you? What J says is the Jacobian of constraints. So if I have got A1 through AR as the active constraints, I will put them their gradients in a row format. This will be my J. This is the case when we have only the active constraints, only the equality constraints. In the bottom case, it says positive definite over null space of Jacobian of constraints that are active at x star, which means that this is for the earlier case. For the second case, you will have to make the Jacobian of constraints of the equality, because all equality constraints are active, and then you will have some C1 and some CT. There will be some active inequality constraints as well. You will put them in your Jacobian matrix. And then what we will do? You will find this null space. You know null space? From your linear algebra, you've studied in your second year. Null space means Ax equal to B, then x belongs to the null space of A. That's what we say. So you find that space. If you can prove that this Hessian is positive definite over this null space, then you're done. Then it's a sufficiency condition. Is that okay? So I've just given you a flavor, because this takes a full lecture, this sufficiency condition. I first explain what is a null space, then I do one example for the equality constraint, then I do one example with the inequality constraint. But I'm not doing this for you because we are not going to use it tomorrow. But you should understand that there is a sufficiency condition in a general case, and it is something to do with the second derivative. Lagrangian तक तो सबको clear है ना? What is a Lagrangian? बस उसका Hessian लेना है. You have to show it's positive definite over some space. If you remember that, that's enough for you, because we're not going to use it tomorrow. If we use it later on, then I'll repeat this part sufficiency with half an hour time so that this gets clear to you. But was the necessary condition clear? That's important. Both with the equality and the inequality, the Karish-Kuhn-Tucker conditions, the cases which we do. Everybody okay? At the back? Yes? So for the undergraduates, non-CS, please, those who are not there, ask them to see my recorded lecture tomorrow. Otherwise, this 5 lectures of SVM will not make any sense. And that is something I teach very rigorously. And they will lose all of it, which means they may actually lose it in the exam also. So give them a little fear. ठीक है कि एग्जाम में भी आएगा और you कर नहीं पाओगे फिर तो पढ़ लो है ना ठीक है ओके थैंक यू